Okay, so I'm going to finish chapter 7. We have a lot more conceptual things to talk about regarding alkenes. So it's been observed that there is this observed order of the stability of alkenes. And I have this written across here. Remember that I'm using R as a generic group of carbons. So this is an ethylene molecule, and so we've just expanded it out so we could kind of look at all of the hydrogens out there. And you'll notice that as we go across, we successively replace one of those hydrogens with a group of carbons, an R group. So in this case, we've replaced one hydrogen with a chunk of carbon. Now we've got two carbons on the same carbon, and then we've got two carbons but on two different carbons on the same side, on opposite sides, then three carbons, and then four carbons. All the hydrogens are gone. Now I've labeled these as A through G just to make it easier to talk about them. Let's think about ethylene as like the parent of alkenes. And so we're going to call this molecule as a monosubstituted alkene. And when you get to C, because both chunks of carbon are on the same carbon, this guy is going to be at the end of a chain, so we're going to call it a terminal, and it's di-substituted because two of the hydrogens have been replaced with chunks of carbon. The cis di-substituted alkene is the next one, so the two R groups are on the same side, cis. On opposite sides, it's still di-substituted, but it's trans. When you move down to three of those hydrogens being replaced with carbon, we call it a tri-substituted alkene, and all four of them, it's a tetrasubstituted alkene. And so this stability is, we're going to read these signs, in math, this means less than. We're going to read it as this molecule is less stable than this molecule, and so forth. So each one of these progressively is getting more and more stable until you get to the tetrasubstituted alkene is the most stable of these alkenes. Admittedly, the three versions of the disubstituted alkenes are pretty close together in stability, but nevertheless there is a noticeable progression. And of course the obvious question is, well, how do we know? How do they figure this out? And they figure it out using heats of hydrogenation. So you can add hydrogen to this double bond and measure the enthalpy of that reaction in each case and kind of adjust it for the number of carbons. So here's kind of a simplified version of that equation without any detail. And so this is indicating that when you say something is less stable, that means that when you hydrogenate it, you're going to get more energy out for doing that. And so we're going to look at it graphically, and we're interested in why is there a difference. And we are talking about double bonds in each case, but it is curious that there's a difference. And so there's two theories to explain that. And one is based on what kinds of bonds you have that are changing in the kinds of orbitals that are being used to make up the bonds around the carbon-carbon double bond. And we talked about the composition of bonds way back in chapter 1. And so if we look at this bond right here, this is an sp3 carbon, and so it contributes an sp3 orbital to make the sigma bond. And the carbon of the double bond contributes an sp2 orbital. So this bond is a sigma bond, but it's composed of the overlap of an sp2 orbital with an sp3 orbital. Same thing here, whereas right here we have one s orbital contributed from the hydrogen overlapping with an sp2 orbital from the carbon. And so the theory is that perhaps the more bonds that we place around the double bond that have the composition of sp3 to sp2 overlap, that maybe those kinds of sigma bonds are more stable than the kinds that you have with hydrogen. That's not a bad idea, but that's not actually the most popular explanation for why we observe this order of stability. So we have this other theory, and it's called hyperconjugation. And so let's take the same alkene, which is, this is a monosubstituted alkene example. And so what I've done is I've taken a CH3 and I've just expanded up one of the CH bonds. And you know this bond can rotate, so any one of these hydrogens come into this alignment. And this alignment, it turns out, is parallel to the pi bond, p orbitals that are making this pi system. And so if we kind of fill in the orbitals now, so we've got this sigma bond orbital parallel to these. And so what the theory is, it's kind of like resonance, but not exactly. If you take these pi electrons and kind of get a little help from this sigma orbital, which is lined up parallel, we'd kind of feed some of this electron density across here. And so in the extreme case, you kind of get something that looks like this, and forgive the drawing, but this is best I could do with the drawing package. But we're saying we get a little bit of double bond character here. And if you think about it, when you do resonance, you're not allowed to move any atoms, and you're not allowed to change the net charge. And in this case, if you took the electron density away from this sigma bond between the carbon and the hydrogen, that would leave the hydrogen kind of out here by itself. And but if you did, you'd create a positive charge on that proton, because you'd take away the electrons. And if the electrons move down here, then this carbon would develop a negative charge. So if you took the whole package, then you wouldn't have changed the net charge. The thing that's different about this is that when we do actual resonance, we never involved any sigma bonds, and in this case we are actually involving a sigma bond. And like I said, it's only a theory, and the reason it's a theory is because, remember, we can't actually take a picture of what the electrons are doing. We can only suppose what they must be doing, or kind of what they might do. And another thing that you might ask is, why would they do that? A sigma bond is a pretty stable thing. And remember, we're trying to justify the observed order of the stability. And secondly, a carbon that's part of a pi system is not got as tight of control over its outer shell of 8 as a carbon that's sp3. And so part of the logic here is that at least when this carbon down here gets that extra pair of electrons, it becomes more in control over an outer shell of 8 than it is when it's just a plain old double bond carbon. So that might have something to do with the driving force here. In any event, the more of this kind of opportunity you provide for the double bond, the more stable it seems to be. So here's the kind of the extreme case, and we don't really see any free protons floating away, which, this implies that it would float away, but it's just an extreme case. So this guy stays right tucked in here close by. So here's my extreme case, and so getting this idea of something like this, if we give more carbon-hydrogen bonds around here, this is going to make more opportunities for this to happen. And so we're going to look for substitution patterns on alkenes, and that should give us an idea about what we can do.
Hi, this is Jennifer from Palais Royal, calling to remind you that Tuesday, March 5th, is your chance to take 20% off almost all of your in-store purchases just for...
Okay, so let's look at some examples. Here is an alkene in this ring, and we want to know the substitution pattern on this double bond. So remember that you need to draw in that there's a hydrogen here and a hydrogen here, and so you've got two hydrogens and the other two positions are occupied by carbons. So this is a di-substituted alkene, and because it's held in this ring, it's a cis di-substituted alkene. If we look at this molecule, we looked at this one earlier also, we have two double bonds in here. And so if we look at this one, there's still two hydrogens on there. Remember, we figured out this one was trans. This is a trans di-substituted double bond. And this one only has one hydrogen left on the double bond. So this one has 3 carbons, so that one is a tri-substituted double bond. Here's another molecule we looked at already. All right, so what is this one? Well, you see that there's 3 carbons, only 1 hydrogen. That one's tri-substituted. And this one is also cis di-substituted. And how about this one? We looked at this molecule and we were looking at E and Z patterns. So if we start going across here, this one there's 3 carbons and 1 hydrogen, so this one is tri-substituted. This one is di-substituted but trans. This one is tri-substituted, there's just 1 hydrogen left. This one is di-substituted and this one is cis. And this one is, you see there's 3 carbons, tri-substituted. Now when I say trans or cis di-substituted, remember that's not nomenclature, that's just, the pattern for the purposes of stability. Something else that we can kind of use to contribute to this discussion, we could go back to some trends that we saw earlier. And so here was our table of bond association energies. And we figured out that we had a difference in stability as we went to a higher degree of CH bond, that the CH bonds got weaker. And we didn't really know why, we just had observed that this trend was true. And evidently it had something to do with having more carbon around the species that you're going to create when you break this bond. And we talked about breaking it homolytically, that is to make a radical. So we're comparing the stability of the quote-unquote 0-degree carbon radical versus primary, secondary, and tertiary. And so we came up with this order based on these numbers. And so since we were talking about this particular table, the data is for carbon radicals. And so we have the inference here that this is the order of stability of the carbon radicals, that a tertiary carbon radical is more stable than a secondary, and so forth. Well, the idea of hyperconjugation can be applied to this, and the same order is true also for carbocations. They both have the same order of stability. Even though this data was for radicals, it still works also that the carbocation order is the same. And hyperconjugation can explain this order because the more carbons, possible CH bonds you surround that carbocation with, the more stability you can impart to that carbon that's got either an empty orbital or a carbon with an odd number of electrons on it. So here's a picture. Here's a carbocation radical, cation, and so it's planar. It's sp2, and so this charge is in an empty p orbital. And if we, so that one's secondary. So if we draw in that orbital and again pull out one of these CH bonds, you see we can get a little assistance from any one of these neighboring CH bonds. Since this one is secondary, there's places where you could get that from either side. So I've drawn kind of this little blurry thing here that shows how you can get some assistance from one of these parallel orbitals. And if this were a carbon radical instead of a carbocation, there'd be 1 electron in here, in which case you'd only make 1 of these electrons to help here, and then this would stay with the hydrogen, would keep the other electron. But again, they don't really float away. It's really still there. But the idea is that the more of those kinds of positions that you surround your carbocation with, the more stable it becomes. So tertiary's got the most opportunities and it's the most stable. Here's the picture with the radical instead. And again, we don't really think there's any free hydrogen radicals or cations going to float away, but it's just kind of an extreme drawing. So let's practice looking at these molecules to see where the most stable carbocations are and to decide what degrees they are. So if we look at molecule A, here's our carbocation. What degree carbon is that? Remember, for degrees of carbon, you just count how many carbons is it directly attached to. So this carbon is directly attached to 1 carbon, so that's primary. And this one is attached to 1, 2, 3 carbons, so that one must be tertiary. And this one is attached to 2 carbons, so it must be secondary. This one is also secondary, and this one over here is primary. Now you notice that in these ring structures we haven't drawn in all the hydrogens on these rings, but when you put that plus sign right there, that means there's no hydrogen here. There's no hydrogen on this one because it's a quaternary carbon, but there are two hydrogens here, here, and here. On this one, where there would have normally been two hydrogens, one of those is missing. So there's one hydrogen here, one here, two here, and two here. All right, so make sure you understand what these little symbols are meaning. You notice that on this one, if I go from this carbon to this carbocation, we lost a hydrogen when we put the plus charge there. Something is missing with a pair of electrons. So out of all of these, who's the most stable carbocation? And remember the order. So it should be the tertiary one, which is the one in B. And then we choose the next most stable. That was the only one that was tertiary. We had a secondary one here and a secondary one here. We can't really tell the difference between the stability of those two guys, so those would be the next most stable. And then these guys are both primary, and again, I can't really tell the difference between those, and so they're the third rank. So I have the most stable, number one. The second most stable are these two guys, and these are the third most stable, or they're the least stable of these carbocations. You notice that all of these guys came from a single structure, and we've just moved the cation around. And here's the original structure. So we just practiced taking off a hydrogen and leaving behind a carbocation off of all those different places. How many points of unsaturation are in that molecule? Well, there's one ring, so that's 1 point of unsaturation. What if we tried this structure? Is that possible? No, you can't have that because that's a quaternary carbon, and you can't put a charge there because that carbon already has its 8 electrons around it, and so no, you can't have that. So there's no such thing as a quaternary carbocation. Now, one other question is, well, all right, so why is this important? Why do we care about the stability of carbocations and radicals and so forth? And so there are going to be some reactions that we look at that go through a carbocation as a reaction intermediate. We've talked about conceptually that some reactions do go through reaction intermediates. And we have several types of evidence that we'll look at along the way that lead us to believe that a carbocation is an intermediate. Sometimes you get more than one product, and the only way that you can explain it is if there was such a thing, a carbocation, and sometimes the products rearrange from what you started out with, and again, the only way you can explain it is with something like a carbocation. And you might not even see how you could get there if you didn't have a carbocation. So here's an example. My goodness, you know, how did you get from a 5-membered ring with this stuff hanging off of it into this 6-membered ring? Well, you know, there you go. How could that happen? Well, it has to be that there was this carbocation and we had a rearrangement. And we're not going to do a lot with rearrangements early on. There's a little bit in the book about examples of carbocation rearrangements. I'm going to kind of sneak up on that and just, I want you to know that it's possible. I'm going to concentrate on other things for a while. But eventually you'll need to sort of come to grips with this whole idea that you can have carbocations causing rearrangements and so forth. And really, you know, this is going to start by protonating this is a Lewis acid base reaction right here. You put this proton here, that gets you a carbocation here, and then this bond is going to move over here. That's going to make your 6-membered ring because that's going to be a more stable carbocation than the one right here. See, this one would be secondary. If I move this bond, then that's a tertiary carbon once that leaves, and tertiaries are more stable than secondaries, and so that's how you get here. But like I said, you don't really need to be able to figure that out right now, but this actually is a problem in the book. All right, another thing, sort of foundation work still. In the previous chapter and a little bit ago, we talked about these trends in carbocation and radical stability. And I mentioned the fact that when you have a reaction intermediate, that was going to kind of have something to do with how the reaction was going to come out. And I made the point of when you have more stable reaction intermediates, you're going to observe more product from that intermediate having formed. But it's logical to ask, well, what does that have to do with it? Because you have to make that carbocation or radical, how does that influence the path? I mean, before you even get there. And when you talk about thermodynamics, that's reaction energy, and so that's the bottom line, but the reaction path, the mechanism, is kinetics, and they're kind of two different things. And so, how can we tie those things together to give us the most information about a reaction? So this guy Hammond proposed a solution to this dilemma, and it's expressed a couple different ways. But let's say that you had two possible pathways for a reaction to go through. And so one way goes through the more stable carbocation and gives you a more enthalpy, in other words, a more exothermic reaction. Or path B goes through the less stable carbocation, and so you get out less energy. And so you're trying to figure out, okay, so how do you get it to go through path A, through the more stable carbocation? And it turns out that, if it goes that way, then you need to understand how did that more stable carbocation influence the path. And that's kind of an astounding thing when you think about it. How did it know? So let's take a hypothetical walk. And this is an outline of our building, the OCSB. Now, I know our class is not in that building, but you've had classes in that building. And let's say that you're in the classroom that's right here in OCSB, and you're going to go to the engineering building. And you could exit out of any one of these doors, or even the door over here, but obviously if you want to get to the engineering building and you want to stay on the sidewalks and you want to get there in the shortest distance, staying on the sidewalks, which door would you go out? And if you think about it, where you're going to go is going to influence what I just said. The door that you choose has been determined by where you're going to go. And so the door that gets you the shortest distance on the sidewalks to PMEC is door C. And if you watch what doors people go out, you might even be able to guess where they're going in certain cases. Again, assuming that they had to stay on the sidewalks. I know that's a constraint that we don't necessarily follow. But if you were constrained to follow the sidewalks, then if you wanted to go to PMEC, you'd go out door C. If you want, or Kirkham Hall, if you want to go to the library, door A is probably your best bet. And if you want to go to CLB, depending, on your preference, door B or A might work equally well, although I tend to prefer B for that. So if you think about it, when you see somebody over in PMEC and you know that they just came from OCSB, you can say, oh, I know that you came through door number C. Well, let's think of these doors like transition states. The door is a passageway to get from this starting place to the product, the destination. And so by the time you make up your mind which door to go out, you've already given some information about your destination. And it's kind of like that with the molecules. Once they've already started to go through the transition state, they already very closely resemble their destination, the species that's the closest to them in energy to the transition state. In other words, you've expended some energy already just to get over the transition state, and so you're going to end up closer to what your destination is. I know that's kind of an abstract, and this is kind of something you may need to think about, but this is a pretty good analogy. So here's some pictures. Um, so when we talk about these energies, I've added some things to the drawings that the book has. So let's say, okay, so here's your starting materials energy value. And it has the opportunity to go over one or the other of these two transition states. And the product of the step is over here. So we have, in both cases, we have an endothermic step. And so if we go over this green path, then the energy value for the product is this energy value, and the energy value of the transition state is here. So the difference between these two is smaller than the difference between where you started and the top of the hill. So what Hammond is saying is that this transition state looks more like this because it's closer to that. Okay, now that was for an example of a fairly fast reaction. Same thing for a slower reaction. Still, it doesn't matter how long it takes you to get there. By the time you get to the top of this hill, the difference between that value and the destination, which is the end of the first step, is that difference is smaller than from where you started. So in either case, the transition state must already look a lot like whatever this is that's the reaction intermediate or the product of that step. Here's some more examples. Suppose that you have a case where you have a reaction that goes through a less stable intermediate. This transition state looks a lot like that, okay? So this transition state is going to look more like this. Whereas if we have the opportunity to have a different path, so this is like the previous slide we talked about path A and path B. This would be path B, a less stable product, that is the reaction intermediate, going through this transition state, whereas we have a slightly slower reaction, but this transition state still looks more like the reaction intermediate. And so this difference is still less than going back to here. So by the time you get over the top of the hill, you already look more like your destination in a case where you're going through a reaction intermediate. Now that wouldn't be true if this were, a one-step reaction and it was exothermic. We're talking about two-step reactions that go by way of some reaction intermediate. We're trying to justify why the reaction intermediate dictates the outcome. And so the more stable carbocation is going to dictate this pathway, because this, by the time you get over the top of this hill, it already looks a lot like that carbocation, or radical if that's what you're going through. All right, one more sort of foundation thing. There was this guy named Markovnikov. This is a Russian person whose name is sometimes spelled with F's instead of V's. But anyway, he was doing some work with alkenes, and he was doing addition reactions where you're adding HX, and X is a halogen, to alkenes, and he observed that the hydrogen went to the less substituted carbon. And I put the hydrogen with the positive character symbol here because if you look at this molecule, there's a polar bond there, and so the hydrogen has some positive character. And so he said the hydrogen went to the less substituted carbon. Now, when he made this observation, people didn't understand the mechanism. It hadn't been generalized at all. He was the first person to make this observation. And it turns out that we now know that the reason that this observation is right and true and reliable is because of Hammond's postulate. And so what happens is that when we talk about this kind of reaction, we could generalize it a little bit more and say, anytime you have an addition reaction on an alkene where you're adding HX or actually a lot of other things, whatever the positive end of the molecule is that you're adding, the thing with the positive character, that's going to go to the less substituted carbon because that will create the more stable carbocation. And we're going to call this guy that's got the positive character, the electrophile. So it doesn't have to be hydrogen. That's just what Markovnikov worked with. Okay, so the electrophile goes to the less substituted carbon so that the more stable carbocation will result. And the more stable carbocation is going to be the more substituted carbon out of the two. Now we need to see some examples of that in order to really understand it, but it can be generalized. So Markovnikov was only talking about HX, but we can generalize his observation by just replacing H with positive character and just calling it the electrophile. You remember we've talked about that definition. An electrophile is somebody who loves electrons, so things that love electrons are things that have positive character. Or another way of saying it is this is the Lewis acid part of this molecule. So here it is again in general terms. When you have an electrophile adding to an alkene, the more stable carbocation, which is the more substituted carbocation, results when you add the electrophile onto the less substituted carbon. That's going to be the first step of the reaction sequence. So that's like all those little graphs that we just looked at. It's just the first step. Then there'll be a second step where we finally get to product. We're not limited to hydrogens, and we're going to see most of these reactions and examples in Chapter 8. Some other terminology. When you talk about Markovnikov, remember this was a case where you had potentially a path A and another potential path B, and yet he observed only product from path A. So in that case, even though you can imagine another outcome, we only observed one. We call that a regiospecific or a regioselective reaction. Okay, so you only get one outcome when you could have had more than one outcome. And kind of where that word comes from is that a specific region of the molecule, in this case the less substituted carbon, gets a specified part of the reagent. And in this case it was the electrophile or the hydrogen with the positive character that was reacting with the alkene. Sometimes you can also have reactions which are stereospecific. So what do you think that means? It's kind of the same thing, only instead of specifying, who goes where, you're talking about the outcome in terms of stereochemistry or 3D results. If you could observe, either an R or S outcome and you only get R, then that's a stereospecific reaction. So what do you need to know? In this chapter, we've already talked about points of unsaturation, specifically with respect to alkenes, but generally, anytime we're referring to the parent alkanes, so you need to be able to take a formula or a structure, figure out how many points of unsaturation there are, or if you have a structure, you can figure out the number of points of unsaturation from that or from a formula. You need to be able to name alkenes and cycloalkenes. There were a few common names that you needed to know, and you also need to be able to apply the cis, trans, or E and Z geometry designations when necessary. And in this section of this chapter, we talked about the order stability of alkenes. So the less substituted alkene is less stable as they get more and more substituted. Remember how many hydrogens have been replaced with chunks of carbon? They get more stable. More substituted carbocations and radicals are also more stable. The stability of all those things is related to the theory of hyperconjugation. So you need to at least have an idea about what that means. You don't necessarily need to be able to draw the pictures. And you also need to be able to understand what is meant when somebody says that this is attributed to Hammond's postulate or Markovnikov's rule. You need to know what that means, and also what we mean when we talk about a regiospecific reactions. And we'll be talking more about those things and looking at specific examples as we go into the next chapter, and that ends this material.